complexity.
Let Tapper take care of this problem.
So,
Passing the buck.
luckily the course has died down a bit and should hopefully stay mostly at that point until close to the end of the quarter, where it will ramp back up for the last homework and the couple projects being due. I mentioned this yesterday, but my recommendation is to knock out that CYK project now or close to now, so that you don't find yourself overwhelmed at the end of the quarter. I would like to have made it due, but I also don't like to force that on people in particular timeframes. So yeah, that's my recommendation. Question?
So we have to do one project?
There are two projects. The second one will be coming. I'm trying to pace the course ever so slightly faster than I have historically, so that we can get to that project with enough time to actually go over the material and give you some time to crank it out before the end of the quarter. Historically, it's kind of been like the Wednesday of week 10, now you're ready to do the project, and I can't really easily make it due by Friday. So it has to be due over finals week, but then there's a final in the class, and I like to either be able to choose, there's a project that's due over finals week, or there's an exam to study for over finals week. I do not like to do both.
Yeah.
So I'm trying to make sure that there's enough time to knock out that second project, because I think it's really valuable. And then have a final exam as well. All right, so last time we started talking about compilers, we talked about what they do. We got partway through this process overview, so I think I'm just going to start over with this process overview, because it's the entire process of what a compiler goes through from start to finish. So it takes as input the source program, whatever it is that you would write, be that a Java program, a C++ program, whatever language you're writing in, feeding it into a compiler for that particular language. And the first step is the scanning step. Question?
No, just backtrack.
Yeah.
I just asked that question because at the very top of the CYK algorithm, it says, remember that you only need to do one project this quarter.
I need to edit that, because that's what I've historically done.
Okay.
Yeah, I need to get rid of that, because I don't like lying to people, and then I also tend to, oh no, I need to reveal this, go reveal it without really looking over everything. Yeah, that's my bad.
No worries.
Historically, I've had one project, but I really think that in the modern competitive industry, the more projects you can have, the more work you have that can show what you know, the better. If that means I cover just a little bit less, but also get a little bit of time to work on the project, I would rather substitute content for something that you can show off that you've done. Yeah, that's a great clarification. I apologize for the misleading communication. All right, so scanning, the process of scanning is going to go through and see a stream of characters, and we want to combine those characters into characters that have meaning, sets of characters that have meaning. This can be keywords, this can be variable names that are in your lookup tables. We'll talk about exactly how those are stored as well. So just grouping things into the associated tokens. And now that you have a stream of tokens, the next question is, do these tokens create syntactic meaning in the language? Do they map to a series of instructions that can be carried out based on the syntactic rules of the language? So do these tokens create a series of Java instructions, statements? So that is the parser's job, is to take the language's grammar and map the stream of tokens into legal syntax, not legal syntax. So as we've talked about accepting or not accepting something in a language, this is very much exactly what that is. We will accept that this stream of tokens represents a program in a programming language, or it does not. If you get an it does not, we can find where in that stream of tokens created the issue. So if you see something like a compile time error of some kind, and you get a line back from the compiler, this is where it was in that stream of tokens when it could not form a valid sentence in that language, or an instruction or a statement in Java, as an example. So it's at the parsing step that it fails. Once we parse it and we get the acceptance from the parser that says, yes, this stream of tokens represents some number of instructions, then we can pass that into a parse tree. So it creates the parse tree, and you pass it to the type checker, which is the semantic analyzer. It's going to go through and say, now, are the variable types for each of these what we would expect? Do these statements have meaning now? It's not, are they just legal syntactically, but can I now carry out these instructions in a way that has meaning? At any point, are we trying to shove a double into a string variable? At any point, are we trying to do some kind of type conversion that isn't allowed? Or possibly would be something that isn't intended. If you've ever gotten a warning from a compiler, this is something that says, I can run this, but it may not be what you intended. Something like if you say, I don't know, I will use a simple example that does not generate a warning as an example. Something like a double variable equals an integer. If you did something like this, then maybe you just forgot to include the point something else. So you would generate some kind of warning that would say, I can do this, but it may not be what you intended. It may not have the intended effect. So the type checker works with the parse tree to figure that out. From there, we go into, we don't modify the parse tree at all at that point. We're just verifying that semantically this works. So we pass the parse tree then onto the intermediate code generator. The intermediate code generator is going to optimize, so I'll get the code optimizer optimizes, but it's going to start to change the structure of your code to map closer to assembly types of instructions. So it will start to do some work on your code in a way that changes however it is that you wrote it into a more standard form of code that is easier to optimize or to determine whether there is an optimization that can be made for it. That intermediate code is passed to the optimizer, which will then modify your code. It will actually change the order or delete some instructions to create a logically equivalent program that runs faster or has less useless garbage in it that doesn't do anything. Because if we can find that, if we can take a small amount of time to optimize your code in a way that will speed it up significantly when you go to run it, that there's value in that. Especially as we work to get this down into assembly instructions. And this allows us, if you include that at the compiler stage, it allows you to make a very inefficient language that could be easy to program in. Python is an interesting example of this. Not that Python is usually compiled, there are Python compilers, but if you can make it easy to use from the end user's perspective and then optimize it within the compilation step, then you have a language that has wider use for learning, for scripting, and then the compiler takes on some of that work of making it more efficient. At the very end of this process, you get a code generator that now generates the machine code or the byte code or the assembly instructions, depending on what the target language is for your compiler. And the output from the entire process is the instructions in the new language, be that machine code, byte code, assembly, whatever. So more detail for each one of these steps. How exactly does this work? Some examples of each of this. We'll start with just tokens and scanning. You can think of this like the words in English, going from characters, a character stream in a sentence, to blocking out, here are the words in the sentence. And now it's not just a stream of characters, it's now a stream of words. Lists of characters that have some meaning when combined in some capacity. So that's really what we're going to call a token. Some number of characters surrounded by some white space. The white space is meant to differentiate kind of the space where one token ends and the next token begins. Although it's not necessarily just white space for this. There are some times when you can, so for instance, you type while, there's an optional space there, open parentheses, optional space, something, optional space, closing parentheses, optional space, open curly brace. The compiler will be working to try to find where those are. So it is not just white space, but there are places where you could include white space without modifying what the code means. We know that it doesn't matter if you put in between the while and the open parentheses. You can put 5 spaces, you can put 10 tabs, you could put 3 spaces, 4 tabs, and 10 new lines. It doesn't matter how much white space you put in between that, because they will just be tokenized as a bunch of null tokens that get discarded. So that's why you can put as much arbitrary white space in a lot of languages, and it's not actually syntactic unless that white space has meaning. Python, for example, if you don't indent correctly, then it's that is used for what scope that particular instruction is in, and then there's ambiguity on the scope. So you can see that there's, in language design, there are a lot of decisions that are made about how important is that white space, how can you utilize that for different meanings syntactically. But we then can assign tokens some kind of type. A token could be an integer. Maybe you type the number 13. Great, that's a token, but it's a token that has the type integer. You could have a keyword like while or class or return. You could have a variable, something that is unique to this program, has a unique meaning within this scope, within this program. So you may need to break this down further if the user hates white space. So the compiler needs to be able to parse anywhere that the language supports optional white space. You can imagine if there were very specific white space rules in a lot of our languages, that would change exactly how we would have to write code. But if it's not necessary, we like to give the end user more power or more choice where we can. So an example of that would be, this is a perfectly legal line in Java. The user just hates white space, but there are many tokens embedded in here. If we wanted to split this out into those, we would have 4 as a token, open parentheses is a token, I is a token, equals is a token, 0 is a token, the semicolon is a token, etc. But the 10 is a single token when taken together. Plus plus is a single token. So we now have token type tuples. Some nice alliteration in there. Token type tuple list gets passed on in the order that they appear in the program. And that's the next step, is the tokens that get passed on to the parser. So let's take a look at, here is some code. What are the tokens and types that we see in here? You can assume this is something like Python, where we don't need a semicolon at the end of each line.
You assume that sum is integer and then sum equals token plus a 10 are all tokens.
Yeah, it would be a variable, but it would be a more specific variable type depending on the type that was declared. Although Python doesn't declare types, and you can reassign types very easily. So sometimes you have kind of an unknown until you get to the execution of the statement, where in something like Java, if you declare int sum, then you can see right when you do this, if total is not an integer, then you might end up with some kind of type clash. Either in the evaluation of total plus 10, or in the attempt to shove whatever that evaluates into whatever variable type sum is. Or you might have something like Python, where the interpreter is trying to figure out what does sum need to be to avoid a type clash. Now it is that if the user intended sum to be an integer, but this doesn't evaluate to an integer, suddenly sum's not an integer anymore. So sum would be a variable, either with a type or without a type, depending on the language. Equals is an operator. Total would be a variable, plus is an operator. 10 is a constant, an integer constant. Green is not a keyword, so it must be a variable of some kind. If is a keyword. 6.5 is a float constant. And 87 is an integer constant. All right, scanning. We need to be able to scan for these tokens. Of everything that we have studied so far this quarter, if you were tasked with making this scanner, how would you do that? What could you use to try to tokenize?
Grammar production and rule.
Potentially. What kind of grammar?
That's a good question. My instinct would say something like context free.
It actually doesn't even need to be that complicated.
It's supposed to be a linear.
Right linear grammar?
Yeah, we can use anything that is regular associated with it. So you would have a regular grammar or you would have a DFA. There are particular tokens that we expect. So if we see character, and we're trying to recognize keywords, we could make a DFA of all of the possible character combinations that lead to keywords or not. So you can feed the characters through that. If it ends in a final state, then it represents a keyword. WHILE. You can imagine now, are there any other keywords that start with W? Are there any multiples that start with, now you just kind of get a web where the final states for each of those can tell you yes or no, this is a keyword or not. If you have, at this point, you wouldn't have a list of variables. If you try to look this up and it's a word that can now pass, you can have a separate DFA that recognizes all legal variable types. Like for instance, can you have a variable that starts with the character double quote? Let's use Java as an example, since we probably know that the best. Can you have a variable that starts with the character double quote? How about underscore? Yes, underscore does work. But there are particular rules associated with how you can specify which characters can appear in which order. Can a number start a variable name? The answer is actually no. But it can be it can be there outside of the first character. You can have temp2 and that's fine. To temp? No. So you can imagine now that you have a DFA that can recognize, is this a legal variable name or not a legal variable? Another one that represents all of the different operators. You see a plus by itself, it represents addition. You see plus plus, and now it is shorthand for equal that variable is a value plus 1. So final states will recognize the actual tokens, and it also tells you if there's something in there that is just garbage. Doesn't map to anything of value in the language. It can't be any reasonable token. So read in each token until you have a set of tokens as identified as something that has value. One of these DFAs returns true. This maps to something that is allowed. And it has a particular type. So you could use a DFA, but everything that we've talked about that has equivalence to a regular language, you could also use. You can now build a regular expression for this, and you can determine, passing this through a regular expression, yes or no, what is this token type? Is it mapped to that regular expression? For each token, compare it to each possible regular expression until you find a match. So regular languages are used as tokenizers. Parsing, on the other hand, the goal of this step was to in comes a stream of tokens, out comes a yes or no, this is legal in this language. So we're gonna pass this stream of tokens through a context-free grammar and determine whether that grammar can build this particular program, yes or no. Is this program a sentence in this language? So we're going to now use the grammar and attempt to derive the program. Which might sound that it's pretty complex because we looked at something like the Java grammar the first week of the class. You can imagine that there are there's infinite legal Java programs. So you can't easily have a process that just starts generating legal programs until it eventually generates yours. We need some intelligent process of which productions should we be applying in attempts to match the grammar to the program. Can this grammar generate that program? We're gonna leave this for the moment, but this is what LL grammars are for, is to make this process efficient. So if we can derive the program, then we know that it's syntactically correct. If we cannot generate the program, then we know that it is syntactically invalid. As we do this, we just build a parse tree of the program that tells us the associated production rules to apply as we attempt to generate the program. Once we're done with that, we have a parse tree that tells us which productions to apply in that grammar to be able to produce this program. So a mapping of the program's instructions to a parse tree. As we start to recognize those rules, we just make branching internal nodes at that point and apply that production. So we have some non-terminal, we identify that we can map this non-terminal and expand it to be some number of terminals and non-terminals from there, and we continue to map that until the leaves of that in-depth first search produce all of the tokens in the matching program. Does that make sense so far? Hopefully everything that we've talked about all quarter is starting to come together as a really why we use this and why it needs to be efficient, because no one wants to attempt to compile their program and wait 10 years to be able to come up with an executable. So we need something that is very efficient, an efficient process for this.
Like it's valid.
Valid, but if you've ever used a compiler, how long does it take to compile your program?
Depends upon the program size. And how many
Don't
times
count
it runs.
IntelliJ because it's doing so much more than actually compiling. It's doing a building step that the compilation is just a small part of.
Plus, if I've compiled this beforehand as well.
Think of compiling from the command line in a Linux environment. How long does it take for a compiler to run? Longest you've had a compiler run on one of your programs. Yeah, anything related to C is built on efficiency. Yeah, if you GCC any C program, the compiler is just, I have it for you, it's right here. It's not using CYK to do that. It's using LL or LR grammars. So if the program becomes syntactically correct, the parse tree is correct and represents the sequence of productions to apply in order to produce the program. Great. We then no longer need the grammar, but we do need the parse tree. We're going to pass the parse tree on to the type checker, because the parse tree can look kind of from the ground up. There are two different processes. One is going top down through the parse tree, one's going bottom up. If we can map, we get expected and declared types as we do this. You can imagine this as a tree. Starting at the leaves, you get something like A plus B. We look at the type of A, since we know that, and we see integer. We look at the type of B, we see that integer. So an integer plus an integer is an integer. If we look at what is, maybe we say C equals A plus B, but C is declared to be a string. Then we get string equals integer. So the top down is looking at what are the expected types, and the bottom up is what are the calculated types. As we meet at a middle node, we need to determine yes or no, this maps semantically or not. So that's what the type checker is doing. It's running that top-down, bottom-up process, mapping, ensuring that types match throughout the program. If types don't match, then we pause this process, spit back an error.
Technically get in from a string, it's all encoded in some integer form.
Right, so the question is just, does the language allow for that? We actually find that in language design, there are a lot of design decisions like, should we allow that? Sometimes there is a one-to-one conversion that you could make. The question is just, is that what the programmer intended? You do not want your compiler doing something that you didn't intend. Some languages will just do that for you and say, I can do it, I will do it. Hopefully that's what you intended. Some languages some compilers will spit back out a warning saying, I did this, don't run this program if it's not what you expected.
Thank you, C, you just handed me the rope.
Yes.
Oh, I can do that. Okay.
But you can also imagine someone in CS1 not knowing the difference between, is this what I intended or not? It compiles, so I'm going to run it. Hopefully that's what the professor intended. So different languages can be targeted to different demographics, some that are easier to learn, some that are more powerful, that can handle more types of different conversions, some that are meant for efficiency, some that are meant for completeness, some that are meant to do as much stripping away of types from the end user's perspective as possible so that they don't have to think about it. But the downside to that is if you're not thinking about it, it's easier to make mistakes. You really have to know what's going on internally, otherwise something's happening that you don't expect. So, all right, this is a fake language. Every program needs a main method that is made up of a sequence of statements, each of which must be of the following types. We have an assignment, a print. That's it. That's all we can do in this language. We can assign and we can print. So here's an example program. We declare main, A equals 4, B equals 8, print A plus B. So we can evaluate within that print. That's fine. But imagine now writing a context-free grammar for this language using these non-terminals. So this will be a class exercise for all of us. You want to be able to use program, sequence, line, variable, integer, and that's it. Those are our non-terminals. So we're going to get something closer to BNF, back as star form, that just says these non-terminals, arrow, some number of terminals, the actual characters that we expect to see. So note that none of these non-terminals are things like the open curly brace or the open parentheses or plus. Those are going to be the terminals in your grammar. The non-terminals are the aspects that have meaning. So an integer is a concept that has a particular meaning. A program is a very abstract concept that has some meaning. So let's define program in terms of some sequence of terminals and non-terminals that's expected. Let's define sequence. Let's define line. So let's take a stab at this and see if you can come up with a context-free grammar that would map to any legal program in this very simple language. Take a few minutes, talk to your neighbors, ask me any questions, any clarification or getting started questions you have. We'll see if we can crank this out. What do we have to start? Let's at least get the first one. If we're doing this in BNF, instead of writing an arrow, there's a colon equals. But I'm still gonna write it as an arrow because that's what we're used to. So non-terminal program, how are we defining what a program consists of? We need to, like, this declares the start of a program, right? So these are all terminals. The concept of main is a string terminal. So we can just write main, open, close, but then what follows that? Of all of these other non-terminals, what represents the most English word for what follows? A sequence. So we're just going to write sequence. And that is the definition of a program. The next line should be some definition for what a sequence is. How do we break down a sequence to be able to get a legal program of an arbitrary number of instructions? We're kind of calling an instruction here a line. So how could we recursively define a sequence in terms of some number of lines? Yeah.
A line followed by another sequence.
So we could have something like a line followed by a sequence.
Or you just end on a line.
Yes, we very much need the ability to terminate. If you just had line sequence, then every single program in this language would be infinitely long. So we wouldn't be able to terminate a program. There would be 0 legal programs in this language. But since we can now terminate it, since a line is a single thing that will break down into terminals, now we can terminate. So you want to use sequence arrow line for the last line of the program and sequence arrow line sequence for any other line, because the sequence tells us that more lines are coming. One or more lines follow.
Starts to look like HTML.
Right?
Yeah, a little bit.
So let's see if we can polish this off. Raise your hands if you think you have something that works, just to get a sense of how close we are. We'll give you some more time. See if you can continue to define these concepts in a way that could map to this program or any other legal program with assignments and prints. I missed one. We're gonna need one more.
Must print to be another program.
Let's go with an expression. And an expression, really, we should just be able to add 2 things. Don't worry about trying to make full expression syntax here. In fact, don't even try to define the expression. You can use it, but don't try to define it. I think that'll make it a little easier.
The terminal for terminal.
Yeah. Or instead of expression, you could just force this to be something like integer plus integer, and that's guaranteed to be the only legal expression type in this language. Question.
Oh. Have an idea.
Oh, yeah. I think we can talk about it.
So what I did is I said that line can derive either just a single variable, or it can derive variable followed by another sequence, followed by another variable, followed by a sequence, followed by the expression of the two variables.
Interesting. Okay. That's a little bit more complicated than I think I was intending with regards to the simplicity, but that would probably work to try to get more complicated syntax in there.
I pretty much just said a line is defined as an variable equals an int, or
Yeah.
it is print. And then expression inside
Yeah.
the parentheses.
Yeah. Yeah, I think that's the simpler way to, we certainly could expand this to allow for much more and much more realistic complication. But in a toy example like this, I'm going for something like this. If we wanted to define expression at this point, we could just say it's integer plus integer if we really wanted to. But yeah, we really just need to define line at this point, and that an integer can be, we can still go down and define what an integer is, but you actually did that already in one of your homeworks. I think it was homework 2.
See previous example.
Yeah, yeah. So there are still a few things that need to be fully expanded here. An integer can be, like, we need a digit, and then an integer is either a digit or a digit followed by an integer.
I think I said variable can be anything inside of the alphabet, and I just defined it for this alphabet, it's just A or B.
Yeah, exactly. So you would need to place some restrictions on this to be able to know exactly what is allowed or not allowed. But this is an example of a grammar, and you can imagine now mapping this program to this grammar. So let's go look at what that mapping actually looks like as we start to build a parse tree from this grammar to be able to produce this program. So derivation of the parse tree would look something like this. That gets expanded into a parse tree. So we start with the program. The program gives us main and the open and close parentheses, followed by a sequence. And so this gets expanded now into sequence, and a sequence is defined to have 2 components. We're breaking it down into sequence is line sequence. So this line sequence now becomes the new thing. This line becomes an assignment. This assignment becomes A and 4. This sequence becomes line sequence. This line becomes assigned B8. This sequence becomes a single line, which becomes a single print, which becomes plus followed by A and B. This is going to be not in infix, but probably in either prefix or postfix, some kind of parsable form for expression analysis. So we can see that we end up with some kind of parse tree that maps to this particular program. And if you read this in depth first search order, you see that the very first thing we do is assign A to 4, then we assign B to 8, and then we add A and B, and we're done. this maps to the exact instructions that were given on the prior slide as the program that was written. You can imagine if all programming languages had you, instead of writing a program, had you writing a parse tree instead. You actually utilizing the grammar to create the instructions that you meant. That would be really arduous. So it's good that we have some programs that do that for us, so that it abstracts the complexity of how to break it down and break it apart legally, so that you can just think about abstractly, what is it that I want to do? Assign, print and addition. It's a much simpler way of thinking than what's actually going on underneath the hood. So traversing the parse tree to determine the program output is a depth first search or a pre-order traversal. And it all comes together. All of the uses of trees from data structures, searching algorithms.
So in the pre-order traversal, each of the leaf nodes become a machine instruction? Basically.
Yeah, basically. That we have the ability to do that, and if we can even break it down, assign is still an instruction.
Yeah.
And then we end up with a and for, so that breaks up the assign this variable, this value.
It's like
Yeah.
move A into forest memory location.
Yeah, exactly. Yeah, so yeah, you can read this parse tree and it starts to break it down into assembly types of instructions. Yeah. So that's the process of getting to the type checker. Once we've made the parse tree, we can pass the parse tree onto the type checker. Type checker looks for semantic errors. Some semantic errors are irrecoverable, like a type clash. If a method takes two parameters, an int and a float, and it passes something like an int and a string, then that's something that is irrecoverable. Some of them are technically semantic errors, but the language has some definition for how that is handled. So a method takes two parameters, an int and a float, and it's passed an int and an int. We can convert an int into an associated float form, and now we allow the user to type an int when they really mean a float. You can imagine languages where you might actually have to declare a float type for every float and utilize an actual float. So if something takes a float and you want to pass it exactly 3, you have to pass it 3.0 or 3 point. Yeah.
So when you're making the parse tree, our expression, like our little expression production, that would be like anything plus anything, and then after the type checker goes back and looks at
Right.
what's actually happening.
Yeah.
It's not explicitly defined like in production.
Right. So you can imagine that we have something like a string A and an int B. A plus B is legal syntactically. But at the type checking stage, then we would see, what does it mean to add a string and an int? Java defines what that is. You concatenate. But you can imagine that that's not necessarily the case, or that a language has a different meaning, or that a language doesn't allow for that. Those are all design decisions within the language that were made as part of the language's rules. When you use a programming language, you are choosing to adhere to the rules of that language's construction. And as you become better and better programmers, you'll start to learn why you might choose a particular language over another, because the rules of formation of that language allow you to do what you need to do for this. You'll start to pick the language that best maps to the task that you need to do, the efficiency that you need to be able to do it in, and the amount of time that you have to crank out the program that does it. All of those are different constraints on you, the programmer, and an intelligent programmer knows all of the available tools and can select the appropriate tool for the task at hand. The reason so many different programming languages exist, and we don't just all use Java, is because there are strengths and weaknesses. There are decisions, and some of those decisions are relevant at certain times. You want to choose a language for some reason or another. Don't just know one language and use it for any problem that you would want to solve. Try to, and I really wish Eastern did this, had an actual programming languages course to go through the different design decisions that are made as we select programming languages, as we as developers can choose which language maps to what kinds of problems and how and why. So you want some fun, not so fun reading to do over the summer, I recommend reading a programming languages book. I have a couple of them in my office that I can recommend. So what do we do? If we convert the int here into a double form or a float form, then that works. But it's on the compiler to recognize, yes, if we're past an int and an int, and the parameters required for this method are an int and a float, then go through the conversion. If we're past an int and a string, then don't attempt to go through a conversion, instead throw an error. So those are rules that are embedded inside of the compiler's code. And the compiler is written to adhere to the language's rules. What is legal in that language or not legal in that language? What is frequently intended in that language or not frequently intended? If you ever find yourself frustrated at a compiler for some reason, it's just not doing what you want, it's throwing warnings when you don't want it to, you can change the associated compiler. A lot of these compilers are open source. You can go make changes to them for your own personal benefit. Make them more complete, make them more robust, make them change how they operate that better maps to how you want feedback from a compiler. There are standard compilers for a lot of languages, but they're not the only compilers that have to exist. Someone wrote it. You can write another one. You could write a different one. Something that is more efficiency tailored, something that is more completeness tailored, that's going to go through processes that actually looks for, can we map this onto some instruction in some other way that allows me to type things differently? It's kind of cool. And that kind of idea is what leads to creating your own programming language. You will find that there is some use case that no programming language out there perfectly fits. Maybe that's the inspiration for, I should write a language that does do this in exactly the way that I want for exactly the use case that I'm looking for. This is why new languages pop up. What language do you want to use if you're writing embedded code? What language do you want to use if you want to write multi-platform code? When you care about efficiency, both from the programmer's perspective or from the runtime's perspective. So we'll come back to this tomorrow and continue and finish this off and move into how to do this process effectively. We'll spend the rest of the quarter really honing in on the parsing process of this, because it covers a lot of the context-free grammar, and a lot of the difficulty in a compiler is writing the parser. So we'll hone in on that as the next step after we finish this, but we'll start that process tomorrow. Yeah.
So if you're talking about the intermediate code generator, what kind of language would that make or use? Because you said that the assembly comes later, so it's not.
Yeah, it's within the same language. So actually the very next thing we're going to talk about, I can very briefly go through this idea real quick. Something like you want to turn something like this into something like that, where we don't easily have assembly instructions for large scale expressions. So starting to map more complicated expressions down into expressions that map more easily or similarly to assembly instructions. Or those that go through, so this is the intermediate code generator, and then the code optimizer is going to take something like this and turn it into, yeah, like you can imagine the prior codes, the code on the prior slide, where suddenly now this is 4 instructions that utilize 4 variables, and this is now 3 instructions that utilize 3 variables instead. And it's exactly the same logic. And there's nothing about how you write Java that forces you to write optimized code. So the compiler will actually go through and optimize your code so that it runs faster, uses less memory, et cetera. So you, the programmer, don't have to think about it.
So the intermediate code generator is gonna likely use the same language that the original language?
Yes,
Okay.
yeah, it's translating language to language, the same language to the same language, but it's just trying to optimize or make it more efficient or better or easier to map onto the target language. Yeah. Yeah, great question. We'll come back to it tomorrow.